Murray, wake up. Murray, wake up. I think we're lost. Oh, should have paid attention to that lecture more. I don't know. It's.
What do you mean we're lost?
It's either Santa Monica or Santa Barbara.
I take a nap for 20 or 30 minutes.
Well, yeah, I was trying.
There's land right over there.
Oh boy, I wish we had that
Santa
lecture.
Monica or Santa Barbara?
Yeah, they're close. They're not that far apart.
You're kidding.
No, I'm not
There's
kidding.
gotta be like 100 miles in between those
Well,
two.
yeah, we got fast engines. It's no problem.
no.
It's no problem. Yeah. No,
Yeah, I know we should have paid more attention at the lecture.
of course, but what are you gonna do? You know, it's lecture's over. We gotta.
No, well, what about you? You're supposed to be driving this thing.
I had an automatic pilot for a while. Maybe the thing steered a little differently. What can I tell you? Maybe.
Wait a second. Wait a minute. Wait.
Call the navigator.
What is that? What is that over there?
It's land.
Wait,
I know it's land. It looks like buildings or
Look at
something.
those buildings.
No, yeah.
What?
I don't know what they are.
No, you're wrong. You're
Yeah.
wrong.
Yeah. Well,
Can't be.
What do you? It's got to be Santa Monica or
Yeah, sure. Just what we need.
Well, it's you know, what can I tell you? It's maybe let's call a navigator. Oh boy, well, it's we're gonna find it. We're gonna find it. Don't worry. Yeah. No, we will. We will.
Yeah.
Look, trust me, will you?
Yeah, just what we need.
All right, I'm good.
I need this to ride with you.
What do you? What can I tell you? The price is right.
I don't care. Go ahead.
I'm good.
Call him. See if I
will.
care. Let me see. How do you
I'm
work
gonna
this
call
thing?
him. You all say we should have watched it. Hey, give me someone up. Send a navigator up. Confirm our.
Tell that navigator to get up here as quickly
No, we're
as
not
possible,
lost.
will you?
Just get somebody up here. Navigator's gonna send an assistant up. He'll be up in a second. Boy, he knows what he's. You don't know
Wait a
what
minute.
you're
It's
doing.
supposed to go up the other way, maybe. What? Oh boy. Look at this. The genius is here.
Well, listen, you know, he paid more attention at the lecture. What can I tell you?
The navigator had to send the assistant.
Well, it could have been worse, you know. The navigator was up, or we'd really be in trouble.
Wonderful. Get him a watch for Christmas.
I hope you got it right.
Well, I certainly hope he got it right, too, because if he didn't, they're going to have one heck of a time trying to figure out where they are. Hi, my name is Gene Grossman, and I'd like to welcome you to our first navigation lecture in our Safe Boating series. And what we're going to do today is we're going to try to give you the basics, just the main elements to get you started in celestial navigation, and try to dispel any fears you may have because of this cloud of secrecy that so many people think has been hanging over the subject so many hundreds of years. And following this lecture, you're going to see Paul Miller do his lecture on latitude and longitude at noon. It's an excellent lecture, and if you follow this one fine, you're going to find out that you know all the words and all the theories you know. You know, many of us have gone to school and our teachers have said to us, don't just try to memorize the formulas. You've got to learn how they make those formulas. So when you're learning the area of a circle or the area of a rectangle, try to understand some of the theory. And that's what we're going to do here. We're not going to get into the complicated aspects of a sight, a noon sight, or how to solve a navigational triangle. All we're going to basically do is show you the elements, show you some of the theories, show you some of the things that apply. You know, a recent dictionary has come on the market with some comical definitions in it, and one of them, which appeals to me, defines sailing, which I believe applies to all pleasure boating, as I believe it's the fine art of getting sick and wet while going slowly nowhere at great expense. And if you have a boat or know anyone that has a boat, I'm sure you can identify with that. But the important thing there is going somewhere. Now, we usually know where we start out because that's in our slip at the marina or the yacht club, or it's at the launching ramp or at the gas dock, and we have a good idea where we're going to end up, maybe at the same place we started or possibly across an ocean. The trick is getting from the beginning to the end of the voyage and knowing where we are all along. And the two tools we need, in addition to a lot of other little goodies, of which there's no shortage if you've ever been in a ship store, is the knowledge of direction and distance. Because with direction and distance, we can always know where we are. And the trick is to know your distance and your direction towards a known point. Now, when we're close to land, we don't have a lot of problems because we can see things. We can see lighthouses, we can see towers, and we can use our charts. It's when we get at sea that's the problem. But there are landmarks we can use at sea. Now, the thing we use for direction is a compass. And there are a lot of histories that have been written about a compass, but one of them, which I think is pretty accurate, is that about 2,000 years ago, in a town called Magnesia in Asia Minor, they discovered that one particular type of metal seemed to attract other pieces of metal. They named it magnetite, from which I'm sure we get the word magnet. And then about 100 or 200 years later, it was renamed lodestone as sort of a nickname. But they found that it would always point to a certain direction. It was sometime later the Chinese discovered that that direction was what we call north now, and they would float a cork in a piece of water with some lodestone attached to it, and it always would point to a certain direction, and I think that's where we got our first compass. Well, nowadays, if you go into a ship store and try to buy one of those, you're going to have a little problem finding one, but they've got some really nice ones that they sell. They're portable ones that you can wear around your neck, and there are some nice ones. This is called a hockey puck, which is a nickname that was given to it, which even lights up at night so you can see where you are. And the main principle is, if we take a look at this figure over here, that the compass card is a circular item which is divided into a lot of small little areas, and those areas are called degrees. And if we count all the way around from one end to the other, we'll find that it's a total of 360 degrees. Now, in the old days, and I'd say it probably still apply right now, they used to have a way they could refer to each one of these. In other words, if it was straight ahead, it was called dead ahead, 1 point off the starboard bow, broad on the starboard bow, but I don't think we have to get into all those definitions now. The important thing is to know that it starts at 0 and goes all the way around to 360. That's the theory. In practice, if you look inside a compass card, inside the compass on a binnacle on a boat or on your dashboard on your little speedboat, you'll see it looks very similar to this. They're all divided into approximately 360, and some of them get rather exotic. They point out the northeast and the northwest and the southeast and the north by northeast. But the important thing is that there's a line attached to the compass called a lubber's line, and that is the boat. And whatever bearing or whatever number points to that lubber's line, that's the direction you're going in. So, if we want to find out where we are, we usually will use our compass and look for a landmark. Now, in this particular drawing over here, we see that there are several ways to do that. If you know the distance and the direction, well, it's very simple to just look at your chart and plot exactly where you are. Unfortunately, we don't always know distance, but we do have the ability to find direction by looking over the top of our compass and getting what we call a relative bearing. Now, let's take a look at what we have over here. We have a situation where your boat is approximately in this point right here, and we want to look at this known point and this known point. Now, if we have a movable protractor or course plotter, and we have our compass and we have our chart, we might be able to find out where we are. What we do is we look off in this direction and take a look at our hand-bearing compass or look over the compass on our boat, and we see that it says a certain amount of degrees. If it says 140 degrees, it would be nice if we could go to our chart and draw a line from where we think the boat is to 140 degrees, but we don't know where to start the line. But we do have an edge. If we know and remember that the compass card was 360 degrees all the way around, and we know that from our boat to the first landmark we looked at was 140 degrees, we then know that there was a direction we can draw a line from that landmark back to the boat. And the trick there is if the number of your compass bearing is less than 180, you add 180 degrees to it. If it's more than 180 degrees, you subtract 180 degrees from it. So if our compass heading says 140, then we know that we can go on the chart and find the landmark we are looking at and draw a line 320 degrees back. Conversely, we do the same thing looking towards the other landmark, turn around, find the return bearing or reciprocal heading, and draw a line back on our chart. And if we do this, and we do it as accurately as we possibly can, where those two lines intersect will be where we are, approximately. But where are we? We now know the directions, and we see where the lines cross, so we can tell approximately what the distance is. But what is the distance? Well, to find the distance, we would use what are called dividers. And on our chart, we would take our dividers, and we would measure off exactly how far we are with the dividers. Then we take the dividers to the side of the chart, and this will tell us how far we are. Now, every nautical chart that we use has on the side degrees, and it also is broken down further into minutes, and every one of those minutes is a nautical mile. Now, most people say, why isn't a nautical mile the same as a land mile, which is approximately 5,280 feet? Well, it's a little more. It's more than 6,000 feet, and it's not that they made the nautical mile longer, it's that they made the statute mile shorter. You see, if you take the entire Earth and divide it into 360 degrees, and divide each one of those degrees into 60 minutes, each one of those minutes is 1 nautical mile. That's the trick there. So we always want to remember that the nautical mile is longer than the land mile, and whenever we talk about miles in navigation, we're always talking about nautical miles. Now, what we want to do is we want to use that information to try to find out distance. When we are at sea, we can't necessarily see lighthouses, towers, and other landmarks. So what we're going to have to use is we're going to have to use a sky mark or some way that we can use a celestial body to find our direction and our distance. And here's how we do it. For instance, in the daytime, the sun is usually visible. Now, the sun has an address, and that address on Earth is the point where it would land if it dropped directly out of the sky. For instance, if we drew a line from the center of the Earth all the way up to the center of the sun, wherever that line crossed the surface of the Earth, that would be the address of the sun at that instant in time. And it's referred to as a GP, ground point, or geographical position. And every sun, star, planet, and moon, which is visible from the Earth by the naked eye, has a GP, the ground point or geographical position with respect to the Earth at any point in time. Now, we have a way of describing exactly where it is. Would you please hand me the chart with the latitudes and longitudes? Thank you, our lovely production assistant. The Earth has some very distinguishing lines on it that we use to find our position. One of them is right around the middle, and it's called the equator. And everything north of the equator is called north. Everything south is called south. That saves Paul Miller the trouble of going into that when we have our next lecture. North and south isn't really the problem. It's easy to find north and south once you know where the equator is. It's going around the other way because there are no real lines around the Earth. So what they've done is, by a convention of navigators, they've decided to use a place in England called Greenwich, which is the town where an observatory is, and they decided to call that 0. And everything going this way is west, and everything going this way is east. And what we have is you go all the way around to 180 degrees west, and from Greenwich you go all the way around the other way 180 degrees east. So you can only go 180 degrees west, and if you go one more degree, you're 179 degrees east. It's just like a forest. How far can you go into a forest? Only halfway. If you go any further, you're coming out. Now, that is our latitudes going north and south, and our longitudes are going east and west. Incidentally, if we take a look at this figure right here, we'll notice that the lines of latitude are all parallel to each other. That's why they're called parallels of latitude. On the other hand, the lines of longitude all come together at the top of the Earth and at the bottom of the Earth. And when you look at it, it looks very much like an orange which has been unpeeled with the slices going up and down. So, if you remember what we discussed earlier, every degree is 60 nautical miles. So you can see that going up will go up 90 degrees, will go down 90 degrees, will go around 180 one way and 180 the other way. But notice, because the latitude lines are parallel to each other, there's the same amount of distance between each latitude line. Unfortunately, though, those lines of longitude, the meridians of longitude, all come together at the bottom and the top of the Earth. And because they come together, they get closer together as you approach the poles. So a minute of latitude near the equator is the same as a minute of latitude either up by the North Pole or down by the South Pole, because the parallels of latitude are all the same distance away from each other. Unfortunately, though, the meridians of longitude are closer together at the ends of the Earth, so that a degree of longitude at the equator is much larger than a degree of longitude when we get down or up near the poles. Now, on a chart, which we use for navigation, on the sides of the chart are the degrees of latitude. On the bottoms of the chart are the degrees of longitude. And that's why I said earlier that when you use your dividers and you found out how far away you are from something on the chart, never use the top or the bottom of the chart. The reason for that being, depending on how far north or south you are of the equator, will change the amount of feet in that nautical mile. But if you use the left or the right side of the chart, you'll always have a constant measurement. And by so doing, we can find our place anywhere in the Earth. So that if you are approximately 33 degrees north and approximately 118 degrees west, then you will be off the coast of Southern California, which we think is a very nice place to be. Now, when we describe the position of the celestial body's GP, or ground point, we call it either Greenwich hour angle or declination. And they're abbreviated as DEC for declination and GHA for Greenwich hour angle. Slight difference being is that declination is the same as latitude. It goes north 90 degrees and south 90 degrees. So as you can see by the figures here, declination and latitude are the same. However, when we describe where the body's ground point is with respect to Greenwich, there's a change. And the reason for that being is that the Greenwich hour angle, or the GHA, is numbered from 1 to 360, just like a circle, which means it will cross over the 180th meridian of longitude. So it'll go 178 degrees west, 179 degrees west, 180, and then the GHA can say 182, 183, or 184, when actually you're 178 east, 177 east, and 176 east. But it's very important that we use the entire 360 degrees all the way around when we discuss Greenwich hour angle. Now we realize that every star, planet, the sun, and the moon have a ground point or a geographical position that we can refer to at any given time, so we'll know where they are. But where are they? Now if I can have my next chart, please. We will use a book called the Nautical Almanac. Thank you. The Nautical Almanac is a publication of the United States government in joint cooperation with the British government. And it is a computerized publication which contains the exact position of the sun, the moon, several planets, and approximately 57 stars for every second of the year. Now, we know they must do this by computer, otherwise there's going to be some guy who gets very tired figuring all these things out, because it comes out every year. But in the back of the almanac, they have a little thing that shows you how to use it from one year to the other. There's some simple formula, which is so simple that I never took the trouble to learn, but I'm sure it's easy to use. Now, the important thing of knowing the exact latitude and longitude, or declination or GHA, of any one of these celestial bodies is this. Once we can measure how far away we are from a celestial body's GP, we will then know distance. Now, if you remember in our first chart, when we had the directions, we said to ourselves it would be so nice if we knew the distance too, but we didn't know the distance. But by using a celestial body, we can find out how many nautical miles away we are. And for every degree we are away, that's 60 nautical miles, because a degree contains 60 nautical miles. Now, we have two things. We have the knowledge that for every degree away we are, we're 60 nautical miles. We also have the knowledge of how to discover at any given point in time exactly where the ground point of the celestial body is. So what we've got to do is we've got to be able to devise some way to find out the distance between us and the GP of the celestial body. Now, looking at the figure, we can see exactly what we were talking about before. If this is the Earth, and this is where our boat is, here's the center of the Earth, there's the center of the celestial body, and this point right here is the GP. And we've got to find out how far away we are from the GP. Moving over to this side of the figure, you'll see that if we draw a line from the center of the Earth through the center of our boat and straight up, that's called our zenith. So what we really want to do is we want to find out our zenith distance. We would like to find out the distance from our boat on the surface of the Earth to the GP. Once we do that, we will know how many degrees it is, and therefore by multiplying by 60 we can calculate how many miles it is. Only difficulty is getting down to the center of the Earth to measure it. Now, in the old days, if you had an expendable crewman, you might want to send him down there, but nowadays with the unions it's really tough, and I hope I haven't offended anyone in a union. So since we can't go down to the center of the Earth to measure this angle, we have to have a second way to do it. And the other way we're going to do it is we're going to measure the angle from our mast, or from the zenith of our boat, over to the same line. Now, a lot of people look at a diagram like this and they say, wait a second. They say this angle down here at the center of the Earth looks like it's smaller than this angle up here. Well, in this particular diagram, the sun looks smaller than the Earth. But in the reality, the sun is so much bigger that all the rays from the sun come down parallel to each other. So it doesn't make a difference if you measure the angle from here or measure the angle from here. The angle will remain the same. Now we have another problem. Don't forget, everything's easy when you're in the slip. But when you're at sea and you're moving around, it's almost impossible to measure the distance from the moving mast or the top of your boat over to the celestial body. So we have to find something stationary. And if you're looking for something stationary when you're at sea, you've got a lot of searching to do. But there is one thing which will always be stationary from us. And you know that whenever you're feeling a little queasy, it's the one thing you look for, and it's your horizon. And here is your horizon right here. And the horizon will always be level for you, depending on how badly your boat's bouncing around. Now, if your horizon goes this way and your zenith goes this way, that forms a right 90-degree angle. Now, if we have difficulty in measuring from our zenith over to the celestial body, there's a little trick we can do. What we do is instead of trying to measure from our zenith all the way over to the celestial body, which is next to impossible, what we measure is up from the horizon. Now, we know that this angle is 90 degrees. So therefore, as many degrees up as we have to come, all we have to do is subtract 60 from it. Or subtract it from 90, rather. Excuse me. It's upside down if it's 60. And then we will know the zenith distance around the celestial body. And once we know this angle, we will also know this angle. And once we know this angle, we will know how many degrees it is, because that's how angles are expressed, in terms of degrees. And once we know how many degrees it is, we will then know the zenith distance, the minutes of arc on the surface of the Earth. As an example, if we measure from the horizon up, and we find that from the horizon up it's 50 degrees, then all we have to do is subtract 50 from 90, and we'll automatically know our zenith distance. It will be 40 degrees. And if our zenith distance is 40 degrees and we multiply that times 60 nautical miles, we will then know that we are 2,400 miles away. Now, the trick is, how do we measure this distance? For that, we use a device known as a sextant. And there are very many different types of sextants. What I have here are the only type that I can afford, which are the inexpensive plastic ones. And I'd like to thank my friend Marvin for letting me use this one. And I'd like to thank my bank account for letting me afford this one. These are both plastic sextants. And if you remember from the beginning of our tape, the gentleman in the orange jacket was holding it upside down and shaking it, and that's really not the way it works in real life. What it does is measures an angle. And the way you do it is you look up, look through it, and through the mirrors, find the celestial body, find the horizon, and by the movable part, the index arm, what you'll be able to do is bring the body down to the horizon. And by so doing, you'll see how many degrees you have to bring it down, and in effect what you're doing is measuring your zenith distance. I'd like to give you a warning. There are some shades that can be pulled down to cover up the reflection of the glare. And if you're looking at the sun, this is very important. And the more expensive the sextant, the more sophisticated the shades will be to filter out the harmful rays. For goodness sake, if you're going to be looking towards the sun, don't use it without the shades down, and then put the shades down to suit you. Start with too many shades, and when you can just barely see the sun, then lift up one shade at a time. That way you won't hurt your eyes. And the one thing you don't want to do is hurt your eyes, whether you're at land at sea. Now, on our figure, we have an example of how to read the index arm. Now, Paul Miller is going to go into this in great deal. I see Paul cringing in the back of the room here because every time I say he's going to go into it in great detail, he has to. He can't make a liar out of me because once it's on the tape, it has to stay there. For instance, let's take a look at this one right over here. As you can see, on our main index right here, the 0 is pointing in between 43 and 44. So it's 43 degrees. Now what we have to do is we look at the vernier and see where the closest point is where the lines appear to be lined up perfectly. And on this particular figure, it looks like the second notch after 20. So every one of these notches is 2 minutes, so it's 22, 24. So this vernier reads 43 degrees, 24 minutes. On the other hand, let's take a look at this one. Here, the 0 is past 44, so we know we're between 44 and 45 degrees. And by looking and seeing it's almost in the middle, we don't have to start searching over here because each one of these is 60 minutes. If it's in the middle, it's going to be close to between 20 and 30. So we can start looking up here, and sure enough, where our yellow marker is, it looks like this vernier reads 44 degrees and 22 minutes. And by doing this, we can see exactly what our zenith distance is, and it can tell us approximately how many nautical miles we are away from the GP of the celestial body we're looking at. And the celestial body can be the sun, it can be any one of 57 navigational stars, it can be any one of 4 planets, or it can be our own little moon. However, just knowing this figure, this HS rather, or sextant height, isn't enough because there are quite a few errors built in. One of them will be an error on the index arm itself. On the arc, you know that when you go to weigh yourself, you'll step on the scale, and sometimes the scale has an error. Now, I've seen this explained many times, and for some reason students have difficulty learning this. It's very simple to remember if you have a weight problem. I'm assuming that includes a lot of the people who are going to be watching this lecture, at least a few of the people I know. And the trick is, if you have your sextant lined up properly, and Paul Miller will teach you how to do that in the next lecture, won't you, Paul? And you notice that you have an error that's on the arc, then you're going to have to subtract that. And what you're going to do is, if I may have the red card with the sample worksheet on it, as you follow through on your sextant readings, thank you, if you'll take a look at these worksheets here, this one right here is a sample of the worksheet that Paul Miller uses. This is the LAN, or Local Apparent Noon worksheet. Here's another type of worksheet, but you'll notice that each one of them does have a section here for sextant corrections. Here's the one on this worksheet over here, which is lines 13 through 19. Here's the one on this sheet over here, altitude, which is the altitude measured with the sextant. lines 16 through 23. Now, as you can see, we have several lines we have to fill in. Getting back to what I said before about the people with the weight problems, if you get on a scale to weigh yourself and you notice before you get on the scale says 5 pounds, I don't think there are too many people that are watching this lecture that would forget to subtract the 5 pounds. Of course, if you notice that the scale says minus 5 pounds before you get on it and then you weigh yourself, there are some people that have slight memory lapses and might not remember to add the 5 pounds to the weight. But that's the same principle with respect to the sextant. If the error is on the arc, it's the same thing as having those 5 pounds on the scale before you get on it. You have to subtract it. And if the error is off the arc, meaning less than 0, that means that with a sextant you should never forget to add it on. And the place that it's done right here is where it says plus or minus IC, and that's your index correction. So you start out with HS, and the HS that you start with is just your sextant altitude. It's your raw measurement. You're going to have to add and subtract some things from it. So we start out with our HS, which is the measurement we got just by looking through the sextant and seeing what the sextant said. Then we have to add or subtract from that our index correction. Next we have our dip correction. Now the problem there is that you aren't at exactly sea level when you're making the measurement. You're going to be at least 5, 10, or on tankers, possibly 20 or 30 or 40 feet above the sea level. And you have to know how high above sea level you are. And for goodness sakes, don't wait until you get out at sea to try to measure how high you are above sea level, because then it's too late. And I'm sure if you remember from your being out at sea at different times, the time to do all your calculations and your measurements is before you leave the dock. It's much easier then. The reason we have to do that is because, if you remember from one of our first drawings, is that we will use our horizon to measure. And if we are measuring an angle up from the horizon, and you're going to be measuring from a certain amount of feet above sea level, this increases the distance around the surface of the Earth that you can see, and it lowers the horizon, and therefore it makes the angle greater, and it decreases your zenith distance. And we don't want to do that. We want to keep that constant. So what we usually do is find out the place on your boat that you will usually be making your sextant shot from. Find out a place somewhere near the stern of the boat where you can hang on to the stern rail rather. Don't forget, it's always one hand for you, one hand for the boat. In this case, it'll be one hand for the sextant and an arm or a hand for the boat, or wrap yourself around the mast in some unsightly position, but hold on closely. And if you've got a lanyard on the sextant, put it around your neck. So if it starts to drop, you don't have to worry about reaching for it. Then you'll have your dip correction, which will always be minus, because you're always going to be above sea level. The only time you'd ever have to add is if you were from below the sea level, and seeing as we don't have many submariners taking the course, yours will always be a minus correction. Then once you correct your sextant for your index correction and for your dip, then you'll have your apparent altitude. Then you have to make a correction if you're looking at the sun, and the reason you'll have to do that, as we see from this graphic over here, is that your shot cannot be to the center of the sun, but that's the way we measure for our ground point. If you remember correctly, I said we drew a line from the center of the Earth to the center of the body we were measuring, but we can't bring the center of the Earth down to the horizon with our sextant. It's too difficult a thing to measure. So what we usually do is we will either use the upper or the lower limb of the body, and we will bring it down. Now, if you are measuring from the edge of the celestial body instead of the middle, there is a correction that must be made. And it's a certain amount of degrees, depending on whether you're using the upper limb or the lower limb, which must either be added to or subtracted from your sextant height in order to give you a proper reading. In the inside front cover of the Nautical Almanac, we have several corrections, which I'll show you in a little while, that you can enter to find out exactly what the amounts are. So don't forget, we have the index error, which it's easy to remember if you can remember the problem of stepping on the scale. If you see it's on the scale before you get on, don't forget to subtract it. We have our dip correction, and don't forget to measure it before you get out to sea. We have our limb correction because we're measuring to, theoretically, to the center of the body instead of to the outer edge of the body. And we have another correction called refraction and parallax. The difference being is that when you are looking at a sunset and the sun is just setting down on the horizon, the truth of the matter is that sun is really gone. It's set beyond the horizon already. The light rays bend. It's the same thing as when you're standing in a swimming pool looking down at your foot. Even though it's only 3 or 4 feet away, because you're looking through the water, it isn't exactly where you think it is. It's always to the side. The light rays are bent as it goes through the water. Whoops. The same thing when we look at the atmosphere. When we look at a celestial body through the atmosphere, quite often the atmosphere bends the rays, so the sun or the body we're looking at is not in the exact same position. And there will be a slight correction for that. Another correction that we have to take into account, more with the moon because it's closer than with anything else, is called parallax. Parallax means, as we showed before, if you're measuring this distance to find your zenith distance, it doesn't make much of a difference if you're measuring from this point on the Earth or from the center of the Earth, because as we talked about, the rays come in parallel to the Earth because the body is so big and so far away. But with the moon, that's not necessarily true. The moon is very small, and therefore it makes a difference if you're way out here or way in at the center of the Earth and measuring. And the best way to explain parallax is by holding 2 fingers up in front of your face and looking out in the distance and blinking your eyes. Now you notice the farther away your hand is, the less your fingers appear to bounce back and forth. And the closer you get, the more they tend to bounce back and forth. And the reason for that is because each eye is located in a different location while your hand is standing still. If you can imagine the moon being very close and you have 2 fingers right here being held up, if you're looking from here or you're looking from here, how the body and the angle which is connected to it will change. Well, there is a correction that must be made, and that's called parallax. It applies to a lesser extent with some of the other celestial bodies. This is the inside of the Nautical Almanac's front cover where they have the corrections. Here's your corrections for dip, which Paul will go into in greater detail, and here's your corrections for your altitude corrections for depending on whether you're looking at the upper limb or the lower limb. Now, what you do is when you take your shot, you will have to know what time you're taking your shot, because just getting a sextant reading and correcting it really isn't enough. The important thing is, as we discussed, is zenith distance is away from a known geographical point. Well, in order to determine where that point is, you have to determine when the shot was taken. Now, for many years, it was very difficult for them to calculate longitude because they didn't have accurate timepieces until a man named Harrison finally came up with the first chronometer and collected his reward from the British government. In fact, that's, I believe, one of the reasons why celestial navigation appeared to be shrouded in secrecy, is because the governments that could do celestial navigation could have their ships rendezvous, which would be a tremendous advantage in military battles. And also in commerce, in commercial business, if you could do celestial navigation, you can have your ships deliver the goods from one side of an ocean to the other in a more expedient way, quicker passage. Now, taking a look, you'll see that in the Nautical Almanac, if we're talking about the sun or the moon or the planets or stars, we have the Greenwich hour angle, we have the declination, and what we have here is a 3-day page, and even hours are given. Now, what hour is really given? That's the important thing. So we have to get into not only direction and distance, but now we get into the third variable, which is time. And time is very important. On most of our worksheets, there are 6 or 7 lines for time corrections. May I have the red one again, please? You'll see. Now, I'm a little bit of a rebel when it comes to time corrections. Thank you. What I like to do is eliminate them completely. Now, most of your worksheets have a way in which you can calculate your local time, your watch error, your zone time. On this particular one here, we have lines 4 4 through 10 for time. On Paul Miller's, because this is for a noon shot, it's shortened down a bit, and we don't have as many time corrections. But we must take watch error into consideration and where we are, and we're not all in the same place at the same time. For instance, the sun, which I will say moves, we all know nowadays that it doesn't. It's really the Earth that rotates, the sun stays still. But everything that I say with respect to the sun and the Earth is relative. So when I say the sun is moving, it's really not moving. It's the Earth that's spinning. Now, you know that there are 24 hours in a day, and there are 360 degrees that the sun must go around in order for it to make a complete day. So if you just take 24 and divide it into 360, you'll see that that sun, with respect to the Earth, must travel 15 degrees every hour. Now, if it travels 15 degrees every hour, you know that it's going 15 times 60 nautical miles. It's going 900 nautical miles per hour. Incidentally, I see so many people, or hear them when we're down at the marina, saying knots per hour. That's a redundancy. And if you really want to separate yourself from the people who don't know anything about boats, don't say knots per hour, because knots means nautical miles per hour. At a speed of 900 knots, that means it's 15 nautical miles every minute. That's 1 every 4 seconds. Now, you don't want to be too far off. Don't forget you're using a sextant, which, unless you're a very wealthy person with one of those $1,000 sextants that can get you within 2/10 of a mile or 1,200 feet, and you're one of us normal people with the type that are less than $20 or $30, you're going to be lucky if the most accurate reading you can get can bring you within 2 miles. So if you're going to be a minute off with your timepiece, that means that you're going to be 15 miles away. Now, that's not too bad if you're looking for the island of Hawaii. In other words, after you sail about 2,200 miles and you don't see land, you just want to know if you're supposed to turn left or turn right. And the sextant will tell you whether you should turn left or turn right. But if you're looking to watch to avoid some reefs or some rocks that are beneath the surface or some dangerous marine navigation hazard, you'll want to know with a little better accuracy than 15 miles. Now, don't forget, we don't want to confuse minutes of arc, which are nautical miles, with minutes of time. But we do want to talk about time. Unfortunately, the time is not the same all over the world. We can't have the time the same all over, simply because it's not true. Instead of looking at our big world map, let's just take a look at a map of the United States at the various time zones. It would be nice to say that they were constant. And when you're at sea, for the greater majority of the time they will be constant, but these are the time zones in the United States, and you can see the way they're rather crooked. I have a suspicion that it's done for geographical reasons, so it'll follow natural divisions between states or rivers or something like that. But the point being is that the sun will travel with respect to the Earth from east to west, and it will be a different time in each one of these zones. Now, when you're on land, it's very easy for you to know what time it is, because you can either pick up a phone and call a local telephone operator and find out what time it is, or listen to a local radio station, or if you have a doubt, you can just stop and ask somebody what time it is, and it won't make a heck of a lot of difference because you're not doing any navigation. But if you're way out here at sea, you won't know which side of a time zone you're on or what you've crossed over. Now, if you're going to use, as they do in the Nautical Almanac, Greenwich time, you're going to have to know what time it is in Greenwich, England. And in order to know what time it is in Greenwich, England, you're going to have to go through what I always consider to be a complicated procedure of transferring your local watch time to Greenwich time. And I have devised a method which many navigators look down upon, but I can't seem to do without. And that is, and I hope this isn't too much of a reflection, I drive our technical directors nuts whenever I do this, is I have one of these watches that's a digital watch and has a digital readout. And it has a digital readout in 24-hour time, which is what Greenwich Hour Time is in. In other words, as we can see by my ship's clock, which I also hope doesn't give too much of a glare, I'll point it down. You can see that starting at midnight, it's the hours around the clock for the first time around up till 12, and then when you get to PM hours, 1 o'clock is 1300 hours, 2 o'clock is 14 hours, and on around to 2300 hours. And as shown on the chart over here, as you can see, it starts out 00 all the way up to 2300 hours, and then when it gets to 2400 hours, a new day starts, and there's your 3-day chart. Now, how do you know when GMT is? Well, it's very easy for me, because when I bought this watch, I set it in 24-hour time to GMT, and I left it there. And I set the date to GMT, and I left that there. Now, this is the watch I use to tell me when to eat lunch, which is always on my watch, and this is the watch I use to navigate with to tell me what time it is, GMT. So I never have the confusion, and I eliminate about 6 or 7 lines of going through. Now, Paul talks about hacking the watch to the radio. You have to make sure that this watch is accurate. Now, most of these computerized chip watches that are digital displays have some sort of small error built in. If you take a look at some of the advertisements of these watches, some will say accurate to within 3 seconds a month, or plus or minus 15 seconds a month. This won't have a great big bearing if you're just a day sailor. If you're going to make a crossing from, say, California to Hawaii, and you're going to be out for 2 or 3 weeks, you're going to want to know a little more how close your watch is. If you've got a watchmaker or a jeweler in your neighborhood who is a friendly sort, what you could do is go there and call up from his place of business and get the time on the radio or the telephone and set a half a dozen of his watches to the correct time, and then go back next week, and the ones that haven't sold, which should be all of them if he's the cooperative type of jeweler, and see which one is then the most accurate with a new phone call to the time beeps. But if you can get one that's fairly accurate, and most of them are over a short period of time, then you can have your little time cube, or your, as you'll see in the second lecture, Paul has his direction finder. You can tune into one of the WWV stations, which gives a time tick every second, and every minute announces the exact time in Greenwich. I believe they call it Universal Time Coordinated now. And you could hack your watch or set it exactly to the time beep, so you always know exactly what the time is in Greenwich. And for a navigator, that's the only time we use. Now, what you do is you take your sextant shot, and as you'll see in the next lecture with Paul, is as soon as you decide exactly when you've brought that celestial body down to the horizon and you've rocked the arc properly and got everything all set, you'll say mark, or you'll quickly refer to your watch. Look at the seconds first, because those are the ones that are moving the fastest, and then it's not going to change that fast. And you'll make a notation of the seconds and the minutes, and you'll find exactly where the sun or the moon or whatever the body is. Now, as you can see on this chart right here, which shows us what the increments and correction pages in the back of the Nautical Almanac looks like. They're the yellow pages in the back of the Nautical Almanac, and as you can see, there are 2 full minutes on each page, and it covers all 60 seconds of each minute. So by using the figures here, depending on whether it's the sun, the planets, or the moon, and using your corrections, as you'll see in subsequent lectures, you can interpolate and get in between the even hours that they give you in the section over there. That takes care of that. Now, of course, the easiest type of shot to do is the one that we'll cover in the next lecture, and that's the one at LAN, which is local apparent noon. And that's by using the sextant and trying to find out exactly when the sun is directly over you. In other words, when the sun is crossing your meridian. That's called a meridian crossing. And if you can find out what your sextant reading is at that time, all you have to do then is look in your Nautical Almanac on the daily pages and use your GMT time and see where the sun was at that second. And that is your longitude. And by doing some simple calculations, which you'll see in the next lecture, you'll show you how to add and subtract and find your latitude, and that will be your latitude and longitude at noon. And that's probably why Paul named it that way. Looking at our next picture here, we can see the dark, deep, and mysterious navigational triangle. And this is what happens, and this is what we have to solve whenever we do a shot of a body when it is other than a meridian crossing. Because then what we wind up with 3 points. One of them is the point where we are. The other is the point where the celestial body's ground point is, and the other point is the nearest pole to the body. Now, depending on what side of the equator we are on and what side of the equator the geographic position of the body is, we will either be on the same side or the contrary side. And the government has put out what they call the HO pubs, if an old Navy man ever explains it to you. And what it is, I think it used to be the Hydrographic Office publications. And they have numbers after each one of them, and each one of them has a different way of solving the navigational triangle. Now, it's just like any other triangle. If you know two sides in an angle or know all three sides, it's very easy to find out where you are. What we'll usually do is, by using our sextant and finding out our zenith distance, we will know one side of the triangle. Also, by knowing the geographic position of the body, we will know how far away it is from the nearest pole. That gives us another side of the triangle. And we will also be able to know, because of what time we did the shot, what the angle is, because the Greenwich hour angle is calculated as that sun with respect to us travels around the earth. And if we know what time the shot is done, then we will be able to figure out what an angle is. And by using the publications 214, 229, 249, and there are quite a few you can use, you can enter and you can find out whether you're on the same side of the equator as the GP of the body, a contrary side, and you can find out exactly what your direction is for plotting purposes. The other thing I'd like to mention is, when you look at the navigational triangle, these lines look curved. They really aren't curved. They're really straight lines. And the reason they're straight lines is because they're all great circles, and that's the way it's calculated. And the difference being is that if we take a look at this graphic over here, you'll see that if you cut the Earth anywhere other than the equator, going east and west, you'll get a small circle. But if the lines of longitude are cut, they each form a plane which cuts the Earth in half, and these are all what they call great circles. And if you look at the great circle head on, it's a straight line. And the navigational triangle, therefore, is straight lines, if there's such a thing as a straight line with respect to boats or navigation at all. Anyway, I hope that we've succeeded in just showing you some of the things that you'll be working with in celestial navigation. Our next lecture, which I can't give too many plugs for, Paul Miller will be taking you through his worksheet step by step in his lecture Latitude and Longitude at noon, which is the most common type of shot, and it's a very useful tool. I'm sure you'll find it easy to work with and you'll like it. And don't forget to watch our other lectures. We'll be doing one on dropping the hook in case you haven't anchored recently. Also, we'll be doing one on using your Loran C, what to do in case of a man overboard, and our trip to Catalina Island, where we'll be tying up at Avalon and walking around, showing you the harbor, how to get in, how to get out, how to get there, how to get back, and where to go on the island. So we'll hope to see you soon at sea or in one of our lectures. Thank you for coming, and have a good sail.
There's one of Paul's boats now. Now that we've finished covering the basics of celestial navigation, let's walk across the street to the marina and see Paul Miller over at the California Sailing Academy, where he's getting ready to give his lecture on a successful noon shot, finding latitude and longitude at noon. Paul's inside waiting for us now.
Anytime we go to sea, we're always interested in getting to the point that we hope to go to. And in order to do this, probably the best method of doing it would be to actually take and use a sextant and measure with certain celestial bodies our position at sea. So what we're going to talk about today is using the sun to obtain our position at sea. In any situation like this, we would go into a chart such as we have over here and talk about latitude and longitude, and that's how we actually get our parameters. So let's take a look at this chart right here. Let's say that that on one particular day we were sailing down the coast and we were up around Port Hueneme up in here. We got a definite fix or position by actually looking at things on the beach. And we were sailing a course of 107 magnetic and at a speed of 7 knots. Well, after a certain period of time, we could then determine by using time against what our speedometer was reading about how far we would be. And also, this course can be represented on here by using this part here called a compass rose. So, at let's say around 12 o'clock, we think we're right here. We depict this with a circle. This circle we call a DR position, or a dead reckon position. We always describe that position on a chart in terms of latitude and longitude. The latitude is measured actually up from the equator, and we always get the latitude along the right-hand side of the chart or along the left-hand side of the chart. In this particular situation, our latitude comes out to be 3345.0 minutes north. Now, if we take a look at our longitude, which is our other measurement of position, this would be 118, this being 118 here, 28.5 minutes over to this point right here. So these two then depict our exact position at sea. All we need is the date, and probably one of my favorite dates is my daughter's birthday. So let's take your form and move into your form that you have, and we'll write in the 21st of July, 1972. So on line 1 of your form, you would write in the day first, the 21st, the month, July, and the year, 72. We also can go right into line 2 now that we have our latitude and longitude. Our latitude, which we just found on our chart from dead reckoning down the coast, would be 33 degrees, 45.0 minutes north. So fill that in to your second line on your form. Line 3 was your 12 o'clock DR longitude. That we determined to be 118, 28.5. And that's in a westerly position. Okay, let's take a look at this graphic right over here, and this depicts our latitude in reference to the Earth here. If you'll notice that what we do is we pass a great circle. Actually, we cut the Earth right in half, and when we cut the Earth right in half, we call that a great circle because it actually divides it in two separate equal halves. This would be what we call a meridian, the meridian of Greenwich, and Greenwich being located right here. That's where we start measuring the longitude. So this point would have 0 degrees of longitude. And then we measure around to what we call the meridian of our position. So here we have our vessel here, and this is the meridian here. And so now we have the latitude, 33 degrees, 45 minutes point north, 0 north that you have written into your form, and 118 degrees, 28.5 west that you have also just written into your form. Whenever we're working with celestial navigation, we're always interested in time. And time becomes something that's quite important. What we've done with the Earth is we've divided the Earth up into sectors. And these sectors are actually what we call zones. And they're 15 degrees wide. I think that what would be well would be to take a look at a globe, and in the globe we will show you these 15 degree sectors. But we have Greenwich, England right here at 0 degrees of longitude. So this would be our prime meridian right here. This is the center of time zone 0. We have time zones that go all the way around the Earth. And so this being 0, this would be +1 time zone. And that's 15 degrees over. So this is the center of the +1 time zone being at 15 degrees west. We also have a negative time zones too. This being the -1 time zone right here, or 15 degrees east. For instance, if you were here in this position, you would have an hour difference between your watch at this location and your watch at Greenwich at this point right here, or 2 hours in here. So this makes it convenient for us to refer back to Greenwich. In Greenwich, is where we keep our time zone of 0, and so as a result we use Greenwich time. And so you'll always hear us talking about Greenwich Mean Time. Unfortunately, Greenwich is no longer on Greenwich Mean Time, but they have shifted over to a daylight savings time actually in the town of Greenwich. So